So, yeah. We're happy to have Inaki do us the next talk.
First of all, thank you very much for the invitation. This is a wonderful workshop. I can't think of a better place to think about physics than going there. So this is something I've been thinking about with Ben Enright and Diego Regalado for the last couple of months or so, and well, a bit more, but there's a different protocol. Basically, we were very curious about something that Mario mentioned on Monday, which is the possible existence of some equals to 4 theories, which have algebra as U2, but they seem to have some different global structures. So we wanted to understand what's going on there. And in part, my motivation would be that. But more than the word, one thing that you observed from Mario was that as they found possibilities that seem consistent, you thought more you found that they actually exist. So for us, that was the motivation to think that, if you have just one pole, one free. Also, the n-2 theories and the particular theory that get from gauging symmetries of this theory should exist. So it's important that theories actually essentially invariant in order to have these symmetries be able to respect to it. Okay, so you're faced with the task of constructing new n-4 theories, and that's well, you don't know where to start. The first thing you can think of, which in a sense works, but you have to start it very hard to know if that works, is the following idea. So I know one way of engineering SUN theories, which is you put type 2 string theory on C2 mod ln times of 4-dimensional math. And it's believed to be the case that as you reduce type 2 string theory on the singularity of this space, you end up with a 60 theory with certain amounts of supersymmetry, leaving T2 type 2. And then, if you make the T2 small, you end up with something equals to 4 theory in M4. And this theory is supposed to have the algebra SU. Now here is where we start getting confused. I'm sure some of you know the answer to this question. This will be very essential, but it's not a trivial answer. So here I was helpful and mentioned this is the algebra of the theory, but you actually want to understand the global structure of this data. So the question is, what is it here? Obvious options are SUN. I apologize, the block is not based on the capital, and I can do fractal, but this is algebra. Or underline. That's algebra. Or it could be SUN on 10, or more recently, Aharoni, Tachikawa, and Seibert showed that there are other cases we could consider are SUN on ZK. And this is at the level of the Kirchner, but there's even extra data. That's the correct case. Yeah. Some decorated group. You can think of this as some discrete theta. So this is the Hardy's side and the reading between the nights. So all these possibilities are consistent with having SUN algebra, and the question is, which one is basically realistic? And the question is important because a very naive thought is that, well, we always say that type 2 string theory is invariant and there are large cubes. So the equality group is the largest group of this T2. And except for some special cases here, so in the particular case of G2 this doesn't happen. For G2, for example, so if I put G2 here, then it so happens that none of these possibilities is invariant under the pole result to 0. So what has happened to the large group of the T2?
So could you repeat again? So you just said that for none of these possibilities,
yeah. So choose
duality.
choose The statement is to do with sample depending on n, so then you choose just n equal to 2, which is in a way the case that Mario and Philip were thinking of. So you choose n equal to 2, and the possibilities are basically SU2 and SU2 minus C2, so SO3. And these guys put the plus and minus, but you can just extend the theta angle, so let's think of it as a single theory. The point is that none of these theories are invariant under SL2. So, for example, I will expand on this in a minute. I take the SU2 theory at the strong coupling, so you apply this quality, and you obtain the SO3 theory.
Sorry, could you just remind the audience how the usual n equals 4 super n mills analysis, just to compare to all these things?
Well, that's part of the point. The algebra is conjecture of chlorides. There are many references to this. But it's not clear which of these possibilities exist. And I will explain in detail which physical data specifies which theory.
But is the usual n equals 4 super n mills part of all these stories?
These are all usual in a sense. The way you specify n equals to 4 theory, up to this, when it works, is that you choose an algebra, you choose a group, maybe you use some discrete theta angles, and that completely specifies the theory. Local operators, combined operators, local operators.
But are you telling, sorry, are you telling us, maybe I completely misunderstood, that for SU2, SL, like S-duality doesn't work?
Well, it's not that it doesn't work, there's a dual description.
Yes.
But you start with the SU2 theory, and so, for example, I'll draw the partition function, I'll explain this in a second. You take the partition function of the SU2 theory with this coupling. This is not equal to the SU2 partition function at top, which is what you would expect from an S-dual theory. It is rather the partition function of the SO3 theory, which is different. It's a totally different function.
Okay. But you are saying that these two things map to each other.
Yeah, yeah. But in order to take the equation that they want, you need actually this equation to hold true.
That's, in some sense, the old prediction from GNO duality. That the SUN global form would be dual to the SUN mod CN.
Absolutely, yes.
Yeah.
But
So it's not an SL2Z duality,
yes.
It's some subgroup of SL2Z.
Okay.
So the things that carry G into itself would only have some finite index subgroup of SL2Z.
Yes.
And the elements of SL2Z that aren't in that subgroup map it into some other theory.
But so why are we surprised that none of this?
Oh, it's not a surprise. At least I was not surprised, I was bothered. From the fact that they have a classification that works beautifully and it has one hole.
Okay, so this is just a statement of how S-duality works.
Yeah, that's
it brings one thing to another.
Yeah, that's it. In general, these two things are different.
Could you say again why you don't care about the difference between SO plus, SO3 plus, and SO3 minus?
Oh yeah. It's just because the difference between those two guys, they will become clear in a second. You can view these two theories as connected by a sheaf of 2 pi or theta. So you can equivalently say that you have an SO3 theory with a theta angle previously 4 pi, and then don't think about two variants because they are connected.
But they have different spectral line differences. So you say.
Well, it's in a very subtle way, right? You just change the monopole with the diode, so that's the shift of the theta angle by 2 pi. There's nothing that you can say perturbative between these two.
So can we just say that the finite index subgroup that carries this theory into itself is gamma of 2, and then we can study, say one can distinguish between the 3 theories.
Yeah, you can do that. I mean, physically, if I give you an SO3 theory, you can see if it's SO3 or SU2, you can line operator very clear, right? But it's much harder to distinguish whether you have SO3 plus or SO3 minus, because you have to decide what you call a monopole and what you call a diode. That's connected by it.
If you make a definition of what you call a monopole and a diode, you can make a distinction between SO3 plus and SO3 minus, but they're continuously related by changing the phase angle.
Yeah,
they're totally perturbed.
Related by T, right?
What's that?
They're related by T.
Yeah, but T is not really.
T
is not something that jumps here. It's not something discrete. It's really something you can do smoothly, and you have a choice.
Right.
You have to decide where you say you have theta equal to 0, theta equal to 2 pi. Right. So anyway, that's not going to be essential for me, so if you want to do this later. It's also not a general thing. So there are cases in which you cannot do this as I said, and you really need to introduce things which are discrete, which you cannot just redefine things to conclude. Anyway, this is the first puzzle. What's the physical data that you have to give in depth to string theory or in the sixth theory in order to specify which of these bits should have. This still doesn't tell you how to persuade self-dual theory, because in the first two cases I just said none of them are self-dual. But hopefully if you understand more, you can get some idea of it. And that seems to be it. The second puzzle is more technical, but I think it's worth explaining. Okay, so you look at that, so it's too complicated, so let's see if this is possible at all. So one thing you can do is look at the paper by Rafa Witten, in which they compute the K3 partition function of the equal to 4 theory with gauge groups SB2 or so these two guys are different. So let's start this for a second. The answer Rafa Witten gives, well, first let's experiment it. In K3, the sort of biggest difference between these two groups is that the instant commanders that you can put on the K3 are different. So, in the case of SB2, you have to put an SB2 bundle. In the case of SB2, you have to put an SO3 bundle. The thing is that every SO2 bundle is an SO3 bundle, but not vice versa. There are SO3 bundles which are not SO2 bundles. So not every. So there are more things you can sum over when you compute the partition function. Okay.
So if you did the computation on flat space,
yeah,
then these two things would
the distinction will disappear. In anything that doesn't have two cycles, the distinction between at the level of bundles will disappear. That's strictly true in the sense that when you put the Wilson line, or the top line is like originally top topology, there is in particular two cycles that links the line. But at this basic level, yes, that distinction. Okay, so what distinguishes an SO3 bundle from an SO3 bundle that's, sorry, an SO2 bundle from an SO3 bundle which is not an SO2 bundle? So this is classified or indicated by something called the sequential universe of the bundle. Let me just spell it. The steeple universe.
Sorry, what's W2?
It's the second Stiefel Whitney class.
Stiefel Whitney. And then I got confused whether Stiefel had two F's or one F.
Sorry, could any of you say, but only one of you say that? Otherwise you...
Absolutely.
Yes.
It's the second Stiefel Whitney class. For example,
It's like
it's basically the characteristic class that classifies the obstruction to lift in SO3 bundle to an SO2 bundle. So we start patchy, where the triple intersections are 1 or minus 1.
So it's just a number, basically.
It's the characteristic class. Yeah, you integrate it over two cycles and you get plus 1 minus 1.
That's a C2 number.
Yes, I see too well.
Yeah, yeah.
Plus or minus 1.
Exactly. Okay, so before we can compute the partition function, and let me first compute the SO3 partition function. And well, this theory is simple enough, and the manifold is simple enough that you can use localization and compute the particular function explicitly. Can be written as follows. So, set 0, this is the sum over bundles that have stable class equal to 0. So, this is basically the part that will survive the message. Then you have the set even and set odd. And the point is that when you have a bundle that has stable winding class equal to 0, these are classified topologically by whether the contribution to the instanton number is half integral or integral. So in the case of the sub 3, it's not the case that every instanton, in the natural combinations of these two, it's not the case that every instanton has integral instanton number. So, set even, roughly speaking, is the sum of instantons such that the instanton number is an integral number, and set odd is when this is half integral. Okay. Anyway, so this is in the classified bundles, and they just sum over all possible bundles that have this instanton numbers. Okay, so now it's just a problem of counting bundles. For the sub 3 case, we have a single bundle. Let's say, here you're summing over SU2 bundles. Since none of them have the non-trivial stable winding class, you have to sum over SU2 bundles. When you do this, you basically have to choose all the stable winding class and then sum over SU2 bundles plus, in a sense, that stable winding class. So here, basically, any one of these is a sum of all instanton numbers. Here's what becomes interesting. So, and even is this is counting problem. So you basically have to choose for each 2 sphere whether you put an unbalancing stable winding class or not. And then you have to understand, not 2 sphere, for every 2 cycle, you have to choose whether you put non-trivial stable winding class or not. And then for any such choice, you have to compute the instanton number and see if it's integral or half integral.
Sorry about that. I still don't get what this omega. Would you mind spending like 5 minutes saying what the winding class is?
How many people know? Maybe you should start with W1.
Yes.
Yes.
Sorry about that.
Yeah, so anytime you have a bundle, you can compute the topological abstraction for the bundle to have some property. Like if you want to see if the bundle is trivial,
Yes.
you can compute the characteristic class that tells you there's an abstraction to globally trivial signal. You can ask if you have a C2 bundle, whether you have any abstraction to trivializing it or not.
So the W1 tells you whether it's orientable.
Okay.
So a priori, you got a real vector bundle with, say, an inner product, and the transition functions are in ON.
Yes.
Right? You can ask, can I put them in SON? Okay? So there's a plus or minus 1 for every patch overlap, right?
Right.
Okay? And that's the first Euclid-Whitney class. If that thing in homology, in cohomology is 0.
Right. So if it is 0, it means
if it's 0, that means that I can consistently choose lift my transition functions to SON transition functions, and the bundle is orientable. There's a common orientation, right? Okay, good. So now the next thing is you can ask whether it admits spinners.
Yes.
Okay. that's an assignment of plus or minus 1 on triple overlaps.
Yes.
Okay? And if in cohomology, Z2 cohomology, that's 0, then you can go to the double cover and lift that SON bundle to a spin-end bundle. Okay, so W2 is the obstruction to emitting spinners. And so in the case of n equals 2, or n equals 3, excuse me, it's the difference between SO3 and the obstruction to lifting an SO3 bundle to a spin 3 or SU2 bundle.
So just to mention, there are generalizations of this quantity for SUM, so you can ask whether you can lift an SUM bundle to an SUM with ZM bundle. Yes. And the idea is the same, you get triple overlaps, and the family we can do that consistently, where these ZM value functions assemble to prepare to something that's proper in the SUM. Yes. Okay. So this is measured by some characteristic class, but you can just integrate it over any 2 cycle, and this gives you a plus or a minus on the 2 cycle. If this is minus 1 in any 2 cycle, then you can lower it to 5. So this is not an SU2 bundle, it's just an SU3.
So maybe a naive question. So if there's an obstruction, so I can't write spinners then?
Yeah.
Then how do I put an n equals 4 theory on this?
No, the spinners of the gauge group.
Yeah, so this is not the Lorentz.
That's what
So
the
not-
gauge group.
Yeah.
This is
So we have a
of the
space-time
bundle. This is the
between us.
bundle over n.
Yeah, this is the gauge group. Yeah, it's where you can choose representations. So over any 2 cycle, this is the fact gives you a number. And there's a way of computing, I will explain later. Given such a assignation of signs to every 2 cycle, what's the instanton number? There's a little formula right there. So once you have that, then it becomes just a quantum problem. You want to know which ones of these give an integer instanton number and which ones give a hard integer. And this is the answer. I don't spend time with that because it's not important.
Why are these prefactors n even, odd, and so forth? Why aren't they part of what you call the partition function? What defines them?
Oh, yeah. So what you have done here is, this is the full partition function, this is the sum of all bundles.
Yes.
And then you have divided the information that specifies the bundle into the information that tells you, first of all, whether the bundle is SO3 or SU2, so whether the instanton of the bundle is contributing here or is contributing here.
Right.
And then you subdivide the information here, in the cases in which the thing is SO3 or SO2, into things that have integral or have interest. And the reason is that apart from the instant number itself, this is the only topological information in these bundles. So any bundle that has the property of being even and has the same instant number will contribute equally to the partition function. So you can write this as sums of bundles, but many bundles will contribute the same function, which is this function. And you just count how many of them are topologically equivalent to one of these. The way we treat things. But it's useful because what I will do in a second is analyze how these functions, which are elementary, if the functions transform under inequality, and I will find the numbers here that make the whole thing inequality right. And then I will try to understand what that means. So here I have gone into a little bit of detail.
And those numbers 22.
Oh, yes. So for example, for a second, 2 to 11. The 22 here is just e to the second Betty number of T3. Because what I'm making, I'm giving a plus or a minus sign to every 2 cycles. So these are all the possibilities. And out of these 2 to the 22, one of them is just 0 to all things. 0 clearly has 0. Well, 0 is clearly even, right? This is no contribution of the trivial bundle. Is 0. So it will go here, but I split it because it's trivial, it's a bundle. And then here comes the counting problem, which ones are even and which ones are odd. So this is solution. So sort of half of them go to the odd ones, not to the even ones. So go to the even ones, not to the odd ones. It's simple calculus, anyone is interested. Just It's an analogous problem of counting the spin structures into dimensions, which probably don't much anyway.
So if we have 22 slots, that's the way of putting pluses and minuses.
Precisely. This is 2 to the 22, and then each of these 22 signs, it will either be an integer one, so there's one of that, the one that's all zeros, or all ones. And then the rest
is the product of all of them.
Yeah.
Good.
And then the rest are split into half integral. And that's not as straightforward to count, but you can count this with once you know the formula for how one such assignation of signs gives you this number. Which I will explain. It's not a complicated formula, but it's not technical. Okay, so once you do, once you're at this stage, you need to compute these functions, right? And this is what often we did. And therefore, This is by the way localization computation. I'm sure some of you here know much better than I do, so you can read paper and start better than I do. In any case, it's not easy to derive, but it's not hard to say. So to explain what Q is, Q is simply this was known, and Q is the data. This is familiar to some of you. And basically, it's a function encodes the remaining sum over instant. So here I just classify with the class, but of course I still have the instant number can be 1, 2, 3, 4, or 3 halves, 5 halves.
This is the tau with tau to tau plus 1 is the periodicity of the plane?
Yeah.
In for SO3?
Yeah, I'm taking the standard.
Okay.
Yeah. So I chose convention in such a way that tau to tau plus 1 will not leave the partition function value. So this is the standard convention, which is SO3 plus SO3 minus.
This is the usual way people define tau for n equals 4. It will differ from the way I would define tau in the afternoon.
Yeah. I think I prefer the other way.
Define it for n equals 2.
Following the master here.
This. Yeah, I mean, my key will be very
Okay. Well, now it's clear what we want to do because we know what eta does and the historicity and historicity. So we have that G tau,
Tau 2 minus 12.
So,
Yeah.
This is 12.
that's right. So, you see already one thing here. You have Q to the 1/2. That's pi tau. I send tau to tau plus 1, the sign flips here. So you send this all to minus 1. So as the distinction between SO3 plus and SO3 minus, basically, in this context.
So, I'm sorry. G of tau, it means G of Q of
Yeah,
Q,
G of
or G of Q to the 1/2?
it means G of Q. I'm choosing, so the real parameter you do is whatever goes into the G,
Okay.
and the notation is therefore, yeah, the hat. And what I mean by this is a function with a Q that's e to the 2 by this time.
It doesn't make it much better because you introduce a new thing.
So the formula is G hat tau.
Yeah, it's the same function.
G hat tau is G of Q.
Yes.
Yes.
Okay.
With a Q. Yeah. I think the right formula because I think it's okay. Anyway, so from these expressions you can see how these factors transform, so you can see how the partition function of the solution. Just for comparing, we expect that the SO3 plus, so the thing as I wrote it there, the strong coupling becomes the SU2, and this is simply 1/2 times C0. So the C0 we understand. This means that we sum for things that have zeros different with the plus, so we are using two bundles. And the 1/2 comes from the fact that when you copy the partition function, you divide by the volume of the H group, and the volume of SU2 is twice the volume of the solution. Because this is just SU2. So the prediction that Bafan will check is that under this duality, this function transforms into that function. Okay, this is essentially true. Modulo 1 small caveat that's basically irrelevant, but let me mention it. So you take theta T2, tau. This is and like Garcia, the one I wrote here with this choice of cells. But of course, the notation is from reading between the lines and everything is consistent. So one thing that I wanted to highlight, just to forget about it later, is that when you do these kind of logical transformations, typically you get the factor in the graph. And the physical reason for this is that when we say the graph n equals to 4 theory, we always think that n equals to 4 theory is flat space. Once you put it in a curved manifold, you have to choose which couplings to R you include. So without putting any couplings, this is the factor. You want to forget about this, you can include, you can take the n equal to 4 action in flat space and the formula. This is standard one, you take it to the standard one plus some things that depend on tau and curvature. So there are choices of this kind of local couplings that vary in flat space that get rid of this conformal part, just to put it out of the way. All these are modular functions, you get functions of tau, but they are physically not very. And then they have that many. Okay. So I'm not going through the calculations because I think that this is very easily clear. We know how the eta function transforms, we know how to express the partition function turns to beta function, so we know how particular function transforms. And now we check why. Okay. So let's do what I mentioned before. Let's assume that there's some SU2 theory. With the hat again.
Sorry, can I ask how is the SO3 plus related to the SO3 minus function?
Yeah, I'm sorry.
How is the partition functions for SO3 plus and SO3 minus related?
So this
Because that's the old switch.
yeah, let me write it. SO3 plus is with distance it's C0 plus C11 plus 0 and the minus and these are exchanged because when you take tau to tau plus 1, you get a sign, this thing gets a sign. You can go through it. Anyway, let's assume that there's a function that modulates modular behavior fulfills this. Locally, the theory is usually 4, but it's easy 2. So, presumably, the function is going to be built of the same ingredients, so things I can believe and things I cannot. And did you know how each of these guys transform? You find that up to rescaling.
So what is SU?
Yeah.
Is SU2?
SU2 that is your proposed theory. It would be a theory that's
Self-proof.
yeah, it's a theory that's completely self-dual.
Okay.
So this gives you two equations. You want this theory with tau plus 1 given the same partition function, and this theory with tau into tau minus 1 over tau gives the same partition up to the modular.
And then then the overall coefficient is fixed by the volume of this.
Yeah. But yeah, I will really not discuss that because the volume of the facet is even clearer without thinking about it. Okay, so you impose this plus so invariance of the whole SMTC, and you find up to the three-factor one solution, which is that okay. So our task, as with this exercise, is understanding how we end up 2 to the 11. Remember that the 2 to the 22 here basically encode the fact that we can't put the non-triviality with Nicholas in any 2 cycle. Here somehow the theory is telling us that if you want to make it self-dual, you have to choose half of the cycles and only put non-trivial stuff there. That's the second question. Last question, remember, was in the 2,0 theory, that to be the only for XP2 times the manifold will be free. What chooses the lower structure of the theory? Turns out that these 2 questions have the same question, which is double square.
So maybe a very silly question. So this 2 to the 11 arises basically because we have this prefactor tau to the minus 12 over there.
You have to put it a bit harder, but if you do you see how the eta transforms?
Yes.
Yeah, it's correct, of course.
Well, we don't need to know how eta transforms if we accept these 2 rules, right? We take these 2 rules and we take a linear combination of these 3 guys such that this is invariant.
It's all equal. It's generated by 3 of them. You can choose either the seeds or just the eta variation.
But since I don't see any 2 to any power in the rules, I was wondering how this 2 to the 11 arises.
Yeah. It's related, yeah. So it's related with it's because the instanton sum here is standard model of all that is.
But again, I don't need to know that. I just take these 3 combinations and I use these 2 rules.
Yeah.
He dropped the ends in that last formula on the right. Even and on. That bottom formula, you had n.
Oh, yeah.
There were the ends there.
Yeah.
But I am not sure how this is relevant. I just take the first 3 things, C0, C even, C odd, right?
Yeah, that's
I
right.
put some coefficients A, B, and C in front.
Right.
I use these 2 rules.
That's right.
And I'm not sure I see how the 2 to the 11 arises.
I don't think I can do in the blackboard because I have notes, but
I see.
the important point is that you know how each of these guys transforms under SN2C.
Well, you just told us, right? It's just these 2 things, like
And then you impose invariant, you impose this two.
Oh, I see. So this, yeah,
There's q's,
Yeah,
a
I see.
square, and a q to the half.
right, and this
So
will
there's going to be a
to-
factor of
to
2 in the
12.
half.
Very
So
good,
you
thank
get
you.
2 to the
Yeah, if you want the information of the K3 itself is built already, each of these guys.
Perfect.
The reason is because you're assuming all the instant contributors.
I see. So it's the fact that we have the square root there, so that is a 1/2 to the 12.
Yeah. That's all related, but the calculation is not, at least to me, it's not obvious that this is the step. So you do it. Okay.
So,
Yeah.
just to see if I understand, you fix now the partition function such that it's self-dual.
Yeah.
It has the same local structure that it had before,
Yeah, the difference is in the sum of bundles, so locally you will see.
but the global structure is none of the two. It's none.
Yeah.
It's no SO2, no SO3.
That's correct. I wrote for you the two
What is
options.
it?
Yeah, this is the 3 and there's the 2.
I think it's a question.
Okay.
Yeah, the question is what is this? This is formally an exercise I've done to a partition function. Like, can I actually construct a theory that
Why do you expect this? I mean, you just impose this. Why do you expect that there exists such a thing?
No, assume the theory exists. This is what this partition
We
function
had
does.
evidence.
No, so the next step is obviously constructing the
It's
theory.
because of the
Otherwise, I would-
We had evidence for
Yeah.
existence of such a theory.
such a thing.
Without understanding.
And it's clear from your construction that it should be self-dual in this
Yes.
sense.
Right. Yes.
Yeah, well, it's not
I
entirely
mean, it's
obvious.
clear, it's strong, but there's evidence that
Yeah.
that has to be something.
Our motivation was
To be clear, we don't construct the theory. We find a certain low energy geometry distinct from the other ones that are known, which
Which is an extra T3
this
as well.
has the full S duality, SL2Z duality.
And so far, all the theories that you have predicted have been constructed, or they haven't been proven not
That's
to
the
be
last
constructed.
one. It's the last entry.
Yeah, it's the black border. So to me, that's very strong evidence that you should think of this theory. Maybe that doesn't make sense.
Yeah, one should try.
Yeah, we spend some time and see to work. But yeah, so this is a formal exercise. If you give me this partition function, okay, fine. Yeah. But there's beautiful physics behind it. So that's one of the papers. Yeah.
So, can you fix the overall constant?
Yes, of course, not from these arguments, but once I construct the theory, I could construct that. Okay, so I think all these questions boil down to one question, which is how do you construct all the n equal to 4 theories with algebra as you equal to it? Right. With the physics that tells you these are beautiful. And in fact, there's an answer. This is what we do. This is, by the way, not the answer to the question of which n equal to 4 theories exist, only the ones that are you in algebra, things that are just troublesome. The best also that paraphrasing Lydia's CFT couple with global development. So basically what I'm going to do now is review this paper. I'm sure many of you know the contents. With that, and to explain that, the recipe I'm going to give later is very magical. So explain how all the known variants fit nicely in floor. And for those who have worked in two-dimensional field theory, this is actually the generalization of what happens in 2 dimensions. So in 2 dimensions, you have the chiral boson, and you say you have the chiral boson in a Riemann surface. That's not enough to say which theory you have. There are many, well, there's more than one partition function that will consistent with that state. And the thing you have to do is choose a spin structure in 2 dimensions. There's something that was long time ago. The thing that we can realize is that these partition functions, well, also Friedan and Schenker and Berlin, realize that these partition functions behave like a vector in a Hilbert space. So there's some operators acting on them, and it's exchange, and things. It's very like a quantum system. And what we can do in the paper of James Moynihan is say, well, these things behave like a vector in a Hilbert space. And this vector in a Hilbert space, actually, the Hilbert space, so the Hilbert space is the Hilbert space of Chern theory. In 3, in particular, if you have the 2D chiral also. On some Riemann surface. Then you have the 3D Chern. We quantize this, and you see that the states of this theory are basically the partition functions of the theories according to the chiral also. So this is from the 80s or so, 70s. Yeah, 70s. Before I was born. And there are many generalizations. It's very important for many things. And in fact, what happens to the universal theory is basically the same. When you think of it holographically, there's an associated 5-dimensional Chern theory that you have to quantize. The states of this 5-dimensional theory are precisely the theories that you have constructed.
I think it might be better to actually say that that's really a feature of the 2-0 theory in 6 dimensions that we started with at the beginning of the lecture. The 2-0 theory is a lot like the chiral boson in 2 dimensions. It doesn't really have a partition function. It has a partition vector.
Intentionally, I didn't do that.
Oh, okay. Well, I'm sorry. it's more. I wouldn't say that that's something intrinsic to 4-dimensional n equals 4 theories per se, which are non-chiral as all hell.
Well, yeah.
It's the chiral theories.
No. Actually, that's important. No. You can understand it as you say. That's perfectly correct, and that's the thing that's closer to the chiral space. It's very chiral. But as I will explain, there's a Chern-Simons coupling the bulk, which is a very SDFT, that behaves identically to the Chern-Simons theory, formally identically, and it gives the same structure also for the first. It's true, you can understand as coming from the 2,0. Yes, but everything I will do is without taking that away. As I will explain, it's sort of very similar, so I could do the same discussion in 16, and perhaps it was more natural, but I didn't want to.
No, it's okay.
Make the
I
thing.
retract.
Yeah. No, it's important because one might think that, okay, maybe this is some crazy thing of the two-dimensional theory that we don't understand, blah, blah, blah. It's hard. But the equation for theory seems to be naked, and it still has this ambiguity. So where does it come? I think that's... but this is more information. I agree with you. Basically, it's maybe more natural. I think this is more information. If you want, I can do the two-dimensional later. Okay. So, good point. Yeah, so as I said, the n-equals 4 theory seems to be naked. Where on earth could be hidden this accelerator and this? And the point is that when you do ADS-50, you say, well, my partition function, maybe a couple of surface, is going to be the expectation value of the fraction. If you want to compute the correlators or some operators in your 4-dimensional theory, you can know it will be the partition function of the bulk with specified boundary conditions. And it seems like this fixes for you the whole theory. But that's not, as we can remark, this is not the whole story, because there's information which is locally not the Etxebarria, but once you have non-trivial topology of the boundary theory, and non-trivial topology is precisely the thing that gives rise in some sense to this stereotypic classes. This non-trivial topology allows you to define gauge invariant operators which are local and not local. So this is nothing mysterious, it's just some sort of periodic variables which are the integral of B2 over some S, and clear. I'm considering holography in some space X5 times S5. X5 is something that has boundary X5. Conformal boundary is my 4-dimensional manifold. So locally, far away, this looks like infinity, this looks like M times R. So this already says differences. And then you have some S in M, which you can view as the asymptotic expectation value on X5. And this gives you one variable. B2 locally is not invariant, so you don't want to give birth to this necessarily. But these guys are invariant. So they are good observables to specify. So when you want to specify the equals to 4 theory in M with a non-trivial topology, you should specify all the spaces. So basically what Newton does in this paper is tell you how to quantize this system in the presence of these spaces. Any questions? No? I hope it's clear. Everything I'm doing is doing it carefully in the case of boundary topology. But we can read it and review how to do this. So let me continue. Here the thing that was playing the central role in having many partition functions was the Chern-Simons theory in the back. In ADS5 we also have the Chern-Simons coupling. Check out where it is. X. And then is the integral of 5 over. So that was Chern-Simons coupling in ADS5.
So now we are about to do a bulk computation. So this is all bulk.
Yeah, yes, this is bulk. I'm going to quantize this Chern-Simons theory in a space-time that looks like a four manifold times R. And I'm going to think of this R as that.
Yes.
And then I'm going to say, as we did here, that the states in this theory are in theory uniform. Oh, yeah. So the goal here, of course, is reproducing the Etxebarria and Montseller theories in this language, seeing them explicitly as states of these Chern-Simons. Okay, so some things are obvious. The equations of motion are the zero. So that's 2. You see that in the usual language, B2 as the two are conjugate variables in the set of quantum dynamics. So you can think of them, one of them as the coordinate and the other one the momentum, for example. And it's the locus of structure, it's low tensor. So once you quantize, you expect to have some commutation operations. Like this. What do we expect in normal quantum mechanics? And of course, momenta combined with momenta and position combined with position. What I'm going to do now is so we can use like 3 different derivations and do the simplest one. It's not the most detailed one, but it doesn't. So let's construct the operators that in this liberal space. This is a Ramon operator associated to any two cycle. Simply the exponential over there. And analogously, there's a Nernst-Box operator related to an integral cycle. And in string theory, you can, this is a system that's ADS5, this is string theory, so you can think of this as the D1 and the fundamental string. Random cycle with the it's a good way. And because of this commutation relation, this operator do not commute. So you have that. This is probably obvious. The phase comes because of this little function. And this is the intersection product of these two things. So how do you interpret this physically? Interpretation. And you have that. Can you all see? Maybe still. Okay.
Can you be again to interpret what did you finish?
No.
No. I was putting it higher because I'm not sure about this. Mysteriously promised. That's it. I read this in office. So this is more or less obvious from this equation. What this operator is doing is measuring the integral C2 over some cycle. The fact that this do not compute, and we can pass this to the inverse here, this to the inverse here, it turns out the depth will be shifted by something, and this something is the 1 over n times intersection. So if you think of C2 as a globally defined form, you're shifting the Poincare involved with C2.
Oh, okay.
And the 1 over n is the 1 over n there, and this is very important. Because otherwise we would be shifting C2 by closed forms integral periods, and that's a Gibbs transformation. But the fact that it's 1 over n, so it's not a Gibbs transformation, it's rather a symmetry.
What's PD again?
Poincare igual. The Poincare igual, so the two forms that the support.
So maybe, so this all stems from the 1 over n in the quantization,
Yes. Which comes from here. Basically, when you write this as x dot times p, you choose your x dot, any of them, and the other one will have a 1 over n.
This is like the 1 over each bar.
right?
Yeah,
right.
exactly. By the way, that's interesting. So here the classical limit is n going to infinity. You forget those steps, and also the SUN and SUN theory, SUN and SUN theories are
Could you remind, us or me at least, what is the Poincare dual?
yeah.
Sorry about that.
The physics way of thinking of this, this is a two-cycle.
Yes.
You can construct the delta function to support on this cycle.
Yes.
That's Poincare. It's something that, if you integrate any of that, it's the same thing as intersecting with the line. Okay, so just the last comment. As I said, this is not the Gibbs transformation for this 1 over n, it's rather symmetry. And you can view that it is a symmetry of the action because the action has an end. So if I send I take that action and I shift like this goes to instant action plus so the fact that there's an n numerator here tells me that I get 1 here. And now I have the Chern-Simons action, one of them being pure Gibbs transformation, so something that's close and continuous. And this is a symmetry of action. Shifting Chern-Simons action by large Gibbs transformation, or a small one is a symmetry. Well, not a symmetry, that's not. Okay, so I will stop here and then I continue with how to investigate this. Okay, so we just saw that in this theory, this Chern-Simons theory, once you contest it, you see that there's an operator that implements some symmetries. This set of operators is sometimes to find, in the sense that they have parameters given by 2 cycles, so 2 cycles combined continuously. So you should ask whether there's an equivalence relation. So first of all, you can see that any of these operators to the end in any surface gives you 1. And that simply goes this, because it's an integral relation, n times the surface. And again, because of this n here, when you want there, the commutation relations are trivial. So in this particular case, it's very trivial, it doesn't do anything. Another equivalent relation is that you have an S such that it's the bound value of Q. Then the operator on S is trivial. And this can be proven easily from the formula. So you could write this as the exponential of using Stokes of the integral of Q of B of B or C equals B. And this is equal to 0 because of the equation of motion. So this is what. Okay. So this is telling me that if I have an S and an S prime that differ by boundary, then I should consider the operators equivalent. This is telling me that I have the surface that is n times on the surface, I should consider the operator trivial. So this is starting to smell quite a bit like H2 of X Cn, these two conditions. And this is a structure we have already seen. So the 2 here, this is the thing that characterizes the Stifler-Whitney process. So it's starting to smell right. What we have done so far is not quite this, because this is defined by the group of chains up to this equivalence, and also a chain should be considered closed if its boundary is n times in one second. Right. In Cn, and this has no boundary.
So just to be, this is the homology, not the cohomology that you really.
Yeah, so they work carefully. I'm going to consider always closed manifolds, which are real towards, or non-concurrent vectors, so be careful. Which way they go. But yeah.
I thought over discrete groups that there was still some.
Not in this case.
No.
Maybe you have no torsion, but consider the whole group. In this case.
This means that the fives live in cohomology, right? Because they're dual to the surfaces.
That's correct. As I said, only careful.
Right.
Something to the right. Okay, but this is not quite it as I said. This group classifies things. So if S has a boundary that's n times one cycle, then it should be also considered part of this thing. And so far I have only considered operators which are closed. So do I have in this theory, or should I do in this theory operators that behave in this way? If I can, then really I should, the operators will do this. As indeed I can, and I should. Remember that I'm doing tech to be in areas 5 cross 5. So, middle picture. If I have some open worksheet, and this E1, I want to see if this can end on something in string theory. There's no like something is n times in 1 second. And indeed, because of the free written condition, this is precisely what we do. If this is D1, this can be n 5 on the internal S5, because we have n units of 5-form flux on top of the S5, that means that you create a charge on this string, and this charge can cancel the insertion of the V1. So, in this theory, string theory to that one, it makes sense to, or you should include these operators, these open operators, as long as the boundary is n times content. This is specifically free to so all this to say that the 5 are classified by elements of this way. These are very different. So from now on, what I will write is, now we're getting close to what we wanted. Remember, this extension was in terms of Stifler-Whitney, and this is precisely what the precisely Stifler-Whitney. As a group, you might think that what you have is an H makes 2, then Cn, Yeah. That's not quite correct. So you think of these as the Ramon operators. So these guys, they're classified by the speed of Nicholas. And then you also have the Neuschwanz guys. But as a group, this is not correct. These guys don't multiply commutatively, because of this equation. So the group that is the symmetry of the theory is some extension of the group by C. This is apparently not a finite Heisenberg. I think it's useful to just to get a good intuition. Once you think of one of these operators of position, the wrong momentum, and you're saying that they don't commute, so the actual group is also the best. So we're almost there. That's the group under which the states of my theory transform.
Sorry, what is W?
Capital W is what?
Capital W is defined by the extension of this. So take the product of these two groups, take the extension given by this non-trivial computation relation, and this defines for your group, which is Etxebarria.
It's a little bit strange writings that way. Those groups are annealing groups under addition. And
Yeah.
here you're talking about multiplication. So those are.
I was expecting you to give me the way.
Yeah.
Yeah, that's true. So think of this, because really what I'm doing is, here this group is an exponential.
Yeah, I
So
know
that's
it's
the
X, but yeah.
It's a little weird, just keep it
I understand that it's a weird way to write it. But
Yeah. Maybe like this.
Yeah, exactly.
Okay. So we have the symmetry group of the theory, and the Hilbert space will be some representation of this symmetry group. It is a true fact that these finite Heisenberg groups have an irreducible representation, which is unique. And this is not so surprising, because if you think of this as the x and p variables, again, it's just saying that the representation of that group is in terms of the x variables and p variables, but they all look the same. They all momentum or position space. The formality varies. So here's the same thing. This is the discrete version of that. And actually it was quite useful. So that's the notation. So mainly you have position and momentum. What do you do? You construct the states in some basis, for example, the position eigenbasis. And then you have two kinds of operators. The position operators, which in this basis they are diagonal. So
What's I?
yeah, it's an example. Which in this basis are diagonal, so that's something like this. So this is the face. And the momentum operators, which in the position basis shift the position. So this is the sort of discrete analogy of that. What I is precisely this composition between position and momentum. It's an analogy. So I is a maximal.
So it's phi sub
That U. exactly.
On both sides.
With, yeah, exactly. With U belonging to I, and U belonging to I.
Right, I see.
Position.
This is something called maximal isotropic subspace. This is a natural notion. A maximal subset of operators that commute amongst each other. So let me repeat that. I is a maximal subset of operators that commute against each other. So the analog of choosing an I is the analog of choosing the position or choosing the coordinates.
So the second one is not that U, for all U not in I, but U in like I per.
Yeah, that's what I'm doing. And sometimes just because this is not full, I will call this polarization. Even if that may be confusing for more mathematically people, for me this is the definition of polarization. Okay, so this is just choice of places. I can construct my field of the space and express it either in terms of the B fields, the C fields. I haven't done anything, just choice.
How do you know I? How do you?
Yeah, that will be basically.
It depends on the manifold.
Depends on the manifold. It's a maximally isotropic subspace, meaning that it's a maximal set of commuting operators, meaning that it's a maximal set of cycles that don't intersect each other.
I see.
Just to, these are generators, right? But somehow, since you are going to generate, I guess, a finite dimension.
This is based on.
For some, are you going to generate a lattice or a finite dimension space or anything?
This is finite dimension.
So there must be some relation, apart from that relation coming from the pi commutation. There might be some relation that makes the space finite dimension. Otherwise, you connect with phi, you have to phi.
This use given a finite group. So the shift is finite. So you have this n times. Here's that. This to the n is 1. So the shift n times.
That's a relationship. The relationship. Yeah, that's a relationship. So there's pi to the.
In the yeah, the operators have that dimension.
Each, okay.
But the Hilbert space is very linear. It's just number.
So just to be clear, in the case of the K3, this group is going to have n to the 22
n to the 11.
elements.
But no, n to the 2. N to the 2. Yeah. So the simplest thing you could do is to advance a little bit. Is either choose the Ramon sector as your position, or the Nelson sector as your position. My point is that there will be other choices, and this will be the simple choice.
I see. So this is the most general setup you see.
So this is the most general. Any
I see.
equals to 4 theory.
Generalizing over the Ramon.
In principle, any equals to 4 theory fits here. Is one of these things. And that's a good question. Nobody has people in this. I'm going to single out some states here because physically they make sense. I'll explain in a second. I don't really know how to do an arbitrary vector in this space, so say the sum of the SU and the SU and the theories. I don't really know what it means. But I'm going to do this more conservatively. So I need two things and then I'm done. First of all, this is just a choice of basis, the way of writing.
What is the polarization?
Polarization for me, because mathematically means different things, for me it will mean the maximal isotropic subspace of this number. So the maximal, physically it will be a maximal set of commuting operators. And the reason this is interesting obviously is because when you're in holography you will put pairs to the fields at infinity. Since these operators don't commute, you cannot just set all fields to 0. At most you can set these the verses of the fields. So I have to choose a state to define my theory. No matter which base I choose, I have to choose a state. Right? So these are independent motions. And it's a true statement that there's a unique state for any choice of polarization I. There's a state omega such that phi of u with omega is omega for u. So this is what I said. Physically, remember, this is something like exponential of the integral or b or c. So if I'm doing a holography, this is the best I can choose a state such that the verbs of b, for example, can choose a polarization, or c are 0 infinity, which means that the exponential is 1. Okay. This is the choice of boundary conditions compatible with conditions.
And you said that for any I, omega is unique.
Yeah. Up to the norm.
So that's
Up to
The norm, of course.
like a vacuum.
is a vacuum.
It's basically a vacuum.
The uniqueness just isn't
I
obvious.
mean, already that there's a vacuum and there's no, this is the operator theory, so like you have excitation.
The uniqueness just isn't obvious.
It's not obvious, I'm sorry. No, I stated it, it's not obvious. You have to say a representation theory here, and you see that it exists.
So how do you do the state out of the vector GTC invariant?
So I don't know if this is what you're asking, but this state is not invariant under all operators. It's invariant under those living in the isotropic subspace.
Oh,
In fact, the others don't leave this state invariant and generate the whole
so
conjugate basis for them.
Is this equivalent to the statement that there's a unique irreducible representation of the hyperliquid?
So you're saying the vacuum is not translation invariant.
well, it's like original.
Representation of what?
So there's no yeah, there's a representation of this algebra, which is unique. And if you choose a representation for any isotropic subspace, there's a representation of the algebra, which is unique, associated to the maximum isotropic subspace. And for any such choice, there's one such state.
I see.
Ideally, should isotropic, but I want to actually do what I can. But yeah, it's still a question. This is explained better in several. So this is the first ingredient in the physics, is that I have to choose something. For me, it will be a choice. I have to choose a state, and I will do that by choosing the polarization, and saying I choose the omega associated with the polarization. And now that physically makes a lot of sense. I'm basically saying this field is going to zero on the boundary. I'm as concrete as I can be by putting fields to zero in the boundary. Okay. So that's one. And once I have chosen a state, I have to construct the partition function. So because now I have proper theory, I have specified data, then I should have an actual partition function. And the partition function here is the inner product of the partition vector. So I need to do that. So I need to express this in some basis. The basis I'm going to choose is the one associated to the Nevers-Schwarz states. Here there's a bit of physics. So far I'm doing some game with Chern-Simons, now I have to actually say that I'm depth to B and things are n equals to 4. And this is what it is. Choose the polarization, which is the normal choice. Polarization. This is really not a very important choice because I could have chosen the Ramon, and by this duality, what I'm going to say will be true. It's just concrete, so it's make present. So associated to this is an omega short. And from here I can construct, so this is such that prime cycle and now let me get the so that's true, that's the defining condition, so I have this described. This exists, constructed. And then I can construct some state U, just the active to the other generators. So this constructs a set of states. And physically,
Those are the same? No.
not yet, but and physically, you should always think of these things as D1s. So what I'm doing is acting on some state by hitting it with D1s, so I'm creating a negative flux. So I'm going to construct a partition vector. This is a vector, this is the number. So in particular, it's transformed into three variable vectors. This partition vector is the sum of the partition functions on the sector of flux U, tau, times this. This is some of the So what am I saying here? I'm saying that the partition vector, the set of all possible partition functions, can be expanded in the basis given by the top fluxes. And the components are the partition function in the sector with top flux specified. So you can do the path integral with a fixed top flux, and this gives you a number. If you sum over them as a vector, you get this. It's probably too magic. So the best derivation I know of this is a paper by Tachikawa from the 2,0. Here I have the video. So you can do this in different ways, but I just give you a heuristic. But you can do it better for that. I recommend take Tachikawa paper. Please take me on faith on this. It really doesn't matter as long as you choose the results of Ramon because this is something that from the algorithm. The important thing is that you can expand the partition vector in terms of partition function and specified topology.
Just, but you're saying that not all pluralization are equal.
No, actually.
You're showing this.
Yes, exactly. I will do it in a second. Now I have the technology for computing the partition functions for two different partitions. You will see one of them is SUN, the other is SUN.
This polarization really is the choice of line operators.
It's related to that. It tells you, yeah. Well, not the polarization itself. Polarization by itself just gives you a choice of basis, but
yeah,
you choose the state as if the polarization, and then you fix the theory, and then you expect the global structure, etc. So everything, all the physics is encoded in this choice of
So for instance, the S dual is the H2 is it?
and that would make sense. Yeah, we will, because that's the next thing. So now you have a physical theory. You have a partition function, specified by the single product. So let's do some examples. I have chosen a maximal set of commuting operators. I can diagonalize them simultaneously and get an orthonormal basis. So this U is the orthonormal basis. So let me choose my correlation to be for any H2. Let me expand omega coefficients in the basis of this. So I need to impose that for any D, this is true. So yes, it's linear inside. And now from the way I have defined things, the Ramon operators here act on the use of shifts. Right? Because if you hit this guy with the Ramon operator, these things add up and the shift is up. So this is C of U of now I can pose this C. There's the question with the components. So this is you can alternatively written as C of U times V of U. So using our for normality, we want to you get that C U is equal to C prime for U. Because this had to happen for D. So we learn that omega is modular prefactor is of V. Which implies that the partition function is the sum over all u's in H2 of the partition function of H2. Yes, the expression, hit it. So this back is SU7 theory. I'm taking the partition function, summing over all possible forces. So, can you
This ground state is the one with respect to this new. This is the Ramon. This is the RR ground state corresponding to.
So it's omega
no,
R.
sorry, yeah, this can be a little confusing. I will fix the base once and for all,
Okay.
which is the NSNS basis. So,
So the omega is the RR.
No.
yeah, this can be confusing. So, the polarization I'm choosing here is the Neo-Schwarz polarization. On this polarization, we construct the basis of the states, which are the U's, without derivating on the omega ns by the R. So that's just the basis. The U's will be my basis forever. The nice thing about the U's is that I can interpret the partition vector in this basis as the one with components of the partition function of the forces. Okay. Now I choose the other one, another polarization.
So this is a different polarization.
Exactly.
And this is the Nova-Schwarz ground?
Yes.
This is the new ground state.
Omega R.
I see.
This is omega R. The U's are the same. The U's are the same, right? But the omega is
Yeah.
no?
Yes.
You just call it omega RR.
Yeah.
Yeah, omega R, for instance.
Yeah.
The U's are the same, right?
Yeah.
Omega.
The U's are the same.
The U's are the same. They are always the same. They will always be the same because they're not the
So that's a U.
Sure.
Yeah. The U's are the same, but the
These
omega
are the same percent. But this is omega RR. This is the defining condition.
Right.
And the use is this. Yeah, I got it.
So now you've rewritten omega RR as a sum with weight 1 over the orthonormal basis of the U's there.
Well, in principle, I have to solve this.
Yeah.
That was the question.
Yeah.
What you find is that omega RR is
is that.
And so so now I don't know, how do you get the implication on the right?
So I have the omega R.
Yeah.
I told you that didn't prove it, that the partition function is the inner product of a partition vector, which is universal, with my omega. So this is where the physics comes in. The choice of theory is sort of inner product of the vector.
So I see. So the partition vector is independent from the choice of those.
Precisely. You can express it on basis or another, but it's a platonic vector.
So the partition function will be that thing, inner product with omega r. That's what you say.
Precisely. So the physics, this depends on the choice of isotropic subspace, and there's an associated state, and this is the partition function to that. For the theory of associated state.
So in particular, so the partition, if you like the NS, with the NS choice, the NS partition function is simply Z sub 0.
Very good. Yeah.
Okay. And here it's, okay.
I was going to leave it as an exercise, but so let me just take it.
What is the last implication though? How do you get the SUM?
Yeah, so here you have the partition function of the N equals to 4 theory, the thing that locally looks like SUM. Some overall possible choices of top fluxes. And that's more or less the definition of the SUM Sudden theory, right? You are taking all the bundles that are SUM Sudden bundles without curve that they give to SUM. If you remember when we did the K3 partition function, it was the sum of 0, even, a lot.
Right.
But that was just a way of splitting the sum of all bundles into segments. The ends in front of it.
And then it was.
Yeah. This reduces the expression problem.
So are you trying to find some S3 and H3 which is invariant of the S2 transposition? That's not what it says.
Yes, this whole business is trying to convince you that there's a. So the thing you should look to is this isotropic subspace, and there's more than the obvious ones, for reasons that are not obvious. Yeah, so Philip already did it. So you have to do the exercise. You choose NS. You can convince yourself that the partition function in this case is at 0. And then this is the SUM. It's nice to do it, it's not hard. Well, so we are almost. I have to prove for you that there's a choice of polarization, which is invariant in research association.
Just very quickly.
Yeah.
So you are thinking that M is always K3? Or are you
No, M. Yeah. So far, M is anything basically.
Because you mentioned the choice of possible polarization depends on M.
Yeah, depends on M percent. But any manifold will have some choice. At the least, you could. So recall that you have H2 Ramon and H2 Neosorption results. So you can always choose one or the other. What I will prove now is that if M is closed on spin, then there are other choices. In particular, the theory that Philippe constructed is a choice of polarization.
Closed means compact.
Compact, yeah. It's a compact.
Compact without that.
No, that's the precise thing, and it's important. So, yeah. Yeah, things are more subtle. Just for simplicity, this is not too important because I don't want to take GeoFrame or something like that. I will assume that also. So what this means is that Hi of a manifold comes from C. This is C to some point. This is a simplifying assumption of physical variable. It just makes things much easier. Okay, so what we need to find, what I will argue, is that then there is splitting H2 coefficients in C into A and B, and these are maximal. And this is surprising, but it was. If this is true,
Zn or Z?
as yeah, right. It's very important because if the n was not there, then not.
If n was that?
If there was C instead of Cn, this would not be true. In general, for example, for P.
What's the bottom line?
Maximal isotropic. So A and B are maximal isotropic. Why is this important? Because if this is true, then I can take a polarization which is A, for example, Neuswartz plus A from. Since A is isotropic, the commutators between the Neuswartz and Ramon settors generally don't commute. But the fact that these commute with each other gives something that makes sense of boundary conditions. I'm supposed to when
When you're done?
I think the idea is
I need to reconsider.
15 minutes?
Like a minute. So this is not obvious at all.
because A is maximum.
Yeah, sorry, let me state the definition because it's not obvious. I'm saying that if you take coefficients in Zn, there's a way of splitting the basis of H2 into two sets which are maximal, which have zero intersection
Among
between among them. That's right. And same for B. So this is for H2, and of course we have an H2 coming from the Ramon sector and H2 coming from the Neuswartz sector. Generally you put either the whole Neuswartz or the whole Ramon. But in this case, since these things exist, you could choose this A from Neuswartz and this A from Ramon. And this is manifestly what it looks like Etxebarria. So let me study this theory and see if it has the properties, for example, K3 of the partition function.
But you're not saying that A and B are unique necessarily.
No, in fact, they are highly non-unique. But it could be, for example, in K3 that they all give the same theory.
Right.
Because there are some huge symmetry groups. The theories are physically distinct.
This is a group of SP, whatever, 2 and 3, I guess.
No, I think the intersection form is symmetric in this case. So it's going to be an O and
Yeah.
kind of duet.
Yeah, if you did the 2,0 probably would be also more applicable because the intersection form is antisymmetric. It will be H3 and then your protocol.
I think I would define these Eisenberg formations.
Yeah.
If n was continuous, you will have SP. Not n, sorry, n was a
Your intuition is basically right. If you do 2,0, you are right completely. Here, since you have the Ramon and the Ramon of the extra sections. The extra torus that you have in the 2,0 is encoded here in the splitting between Ramon and the Ramon. I'm putting this better, but your intuition is basically right. But it works better in the 2,000. So I have a physical algebraic model, right? I have for any spin manifold, I want to claim that I can do such a thing. So in the interest of time, I will just do n equal to 2, so the theory. But this is true also for any, no. The thing is true for any n, but probably for many other n's, like prime numbers, series of prime numbers, series of odd numbers. No respect is true for all n, but not happen for. You will see why you said. Number 3.
Can I ask a question? Is there a notion, I mean, I don't know if it even makes sense, but is there a notion of a size of I, in the sense that, for instance, there's the idea, at least thinking in terms of like line operators, that are kind of like choices of the lattice that are more sparse than others?
Yes, yes.
Is that kind of idea, has any translation?
Yeah, I think the analog here is important this is maximum. I'm not very satisfied with that answer, but still works. Okay, so this is a huge space of spaces, but luckily it reduces to a very tractable. So it is a profile that something called the Hasse microscope classification. That is implies that for any manifold of that kind, the intersection form being next to representing C is the E8 Cartan matrix certain number of times plus H, which is simply 0, 1, 0, and other number of times. So the problem simplifies enormously. You can always choose a basis for this manifold in which it splits into blocks. Some of them are H and some of them are the E8 Cartan matrix. That are very useful. Europe and Now, for
C, nice.
No, Z. This is Z. This is
that's correct. That's it. Yeah.
So, in the K3 example, it's 2 E8s and the rest.
No, it's two,
And 6
it's
H's.
two copies of the 8 and 3 copies of 8.
Yeah, there was.
Yeah.
So K3, you get the 8 2 times, and then you set but this is totally different. And now makes it tractable because imagine that you have just this part, F0 for example. Then manifestly this exists.
It's just sort of, it's actually, usual intersection point is actually minus. So the
Oh, yes.
minus this whole thing.
It won't matter.
It wasn't right, yeah. That doesn't matter for what you're doing, but
Yes, and it's a choice of orientation, as you're saying, but let me just
whatever this is.
But yeah, in the usual conventions, I should have so, assume that there's no gate factor, then this is manifestly of this form. If I choose the first element in the basis that has this intersection form, it has a square equal to 0, and this guy has a square equal to 0. The fact that they intersect is expected. You don't expect momentum and position to come. So already for some manifolds you can immediately see that this idea won't work. Now you can immediately see that this idea will not work for K3 as written, for the simple fact that you want to find vectors such as H square is 0. So imagine that you are looking at an E8 block. The E8 Cartan matrix is positive definite. So you're taking a normal vector with this matrix, but this is only true of Z. Once you go to Zn, it's not. An example is C2. In C2, obviously, the signature doesn't make any sense. I can go from an 8,0 matrix to a 4,4 matrix. And I will just consider right now that there's a change of basis that takes the E8 Cartan matrix into something that's H to the 4. And then we're done. We're almost done. There's one extra technical idea of this guys. So since I don't want to go over time, I will just do the equals to 2 case.
So So it's clear this works, as you just said, for n equals 2, right? Because, precisely because E8 is even.
Yeah.
Even self-dual.
Yeah.
But
It's very simple. So let me write what you have in mind here, because that's what goes me to the exercise. So the E8 part of matrix is on basis is the things I don't write there are obscure.
Sorry.
Yeah.
When K was not 0, so when you had E8s, it's clear that this trying to
I'm sorry.
well, oh, maybe I'm not misunderstanding. Well, the set A or B being maximally isotropic means that the elements have to have length 0
Have to have zero intersection number
with each other, but not with themselves.
yeah, among the sets. So in this context, whether two operators commute is the same thing as whether they have zero intersection number model.
Right.
So all the two forms here have zero intersection number among each other, including squares.
Including your squares.
And the same thing inside the set, but not between elements of the set and the set. The fact is maximal means that once you fix A, anything in B will not commute with some element of it. In other words, it will intersect some element of it. So this is the Cartan matrix. And as I was saying, this is very sadistic. So the 2's go to 0, the -1's go to 1's. So this almost looks like H, and indeed. This is a change of basis.
It's good to have something.
So this is a change of basis. I don't understand this matrix, but
no, I mean, you don't need to write out explicitly. I mean, the E8 root lattice is even self-dual, so the length of the square of any vector is an even number.
Oh, yeah.
And that means it's 0 non 2.
Yeah. No, that's
So-
of course. No,
So right, that's.
I'm aware of that.
Yeah.
No, the point is that modulo 2 E8 can be written as H to the fourth.
Yeah.
And this one.
Yeah.
So this is the matrix that tells you. It just existence proof, this works. There are nicer arguments for prime n and so on, but after we discuss that. Let me just mention one last thing. So once I write every factor like this, then mod 2, then I have that is just H to the K plus N. And now there's manifestly in the structure element, so you could use.
4K plus L.
Sorry?
4K plus L.
Yes. So now in this case the theory exists. So in particular your theories will be constructed. For the experts here, there's something I should have said and I haven't said. The fact that you can write the splitting like this, in this form, and with H like this is all good and improves S duality for you. If you want to prove invariance on the T duality, you do one extra condition, which is that the elements in A have contrarian square equal to 0. I will not discuss this without time. If anyone is interested.
Could you just repeat the condition?
Yes. In order to have full S2C invariance, it needs to be the case that the elements in your chosen lattice have contrarian square equal to 0. Contrarian square, in fact. So you have some element A of H2 of manifold coefficient 2, and then you want to take a square to see that this is. The important thing for invariance under tau plus 1 is whether not whether A squared is equal to 0, which is automatic through the same because it's a string, but rather whether the Pontryagin square of A is equal to 0. So the Pontryagin square is a map from H2 with coefficient C2 to H4 with coefficients C4. And this is important. This is a refinement of the usual square. The usual square, which is this one, is valid in C2. So I know this is too much topology, but anyone's interested, I'm happy to explain.
This is true only for any or two, or?
And yeah, this is most important for even for other integers. Because then even. So here we are doing this A, which A, and this is valid. If anyone is interested, I have to explain this. This matrix I wrote here has that property, so this is full business. I think I want to do rather than doing that. Is computing the partition function.
So, I'm sorry, I'm just not familiar with the Pontryagin map is just the A cap A?
No, it's something that, so A cap A is valid in mod 2.
Right. Mod 2.
This is valid in mod 4, so some sort of refinement. That you take this mod 2, agree with this, but this is automatically 0 to contain no information for speed map. I can explain to you how to compute this, not hard, if you have some notes. Okay, so the partition function. This is already done. I want to prove that the partition function I sort of guessed before from Poisson's Wild is the one that we use. Well, first of all, so I have an omega I, and this is the sum as before of CU U, so zero basis. So remember that here, I simply, once you have gone to the basis in which your intersection form is H to the 4K plus L, clearly there is an A and B splitting, so I'll choose A and B. So A would be this guy, and B would be this guy. So I'm going to choose A, and then there's A and S, plus A and W. So when U belongs to A and S, the condition that of invariance is that phi of U acting on this guy, Now, if you did the exercise that Philip did before, you see that phi of U when it's of the NS sector is just giving you a phase. So this is E I U W.
So W is the U.
W is, sorry, it's just the basis. Here I changed from U because stupidly I started putting U.
So that would be that.
Yeah, U is just the universal basis I chose before. Yeah.
It's just an on the index.
Yeah, it's called W instead of U. It's the same basis as before. Yeah. And everything I'm saying is this is the universal basis, the universal operators act as a phase. It's the diagonal basis. And the phase is the intersection number. Now is where the topology, what this exercise did, bears fruit, because this implies two things. When U belongs to A, when U belongs to A, these intersection numbers and W belongs to A, this phase is R1, and there's no constant. When W does not belong to A, then there's a non-trivial intersection, there's a phase, and there's nothing before. CW is C. Right, so I have to say that this is equal to this. Some of these coefficients get a non-trivial phase. Those that get a non-trivial phase have to be 0 in order for two equations to work. So there was a double phase. So from here, we learn that is the sum over A of CW. So notice that now the state has been restricted. Here is equal to U that belongs to which so this is more some stable phase. But I also has the random on this. So I have to impose that this is the same as this. This acts receive. So this is sum. This is the same thing I have before as well. So we're here I read that all the coefficients are equal. So finally, I get my desired answer, which is that the partition function of my theory with this choice of polarization is the sum over all the vectors in the A lattice of the partition function. Now, two things. But the order is even. This depends on the contrarian square. And the dimension of A is half of the B2, so this is the 2 to the 11. That was all.
That's K3.
Yeah, that's it. So, okay. I'm going to stop here. There's more things to say, but let me summarize it quickly. What I just did was taking seriously this prescription of Witten for constructing all the boundary theories in ADS, a study which boundary conditions exist. Surprisingly, because of this fact, which is very non-trivial, for the spin manifold you can construct one of these theories that you guys were proposing. And seems to have good properties. So I can explain later how. I did this already for K3. Actually, from the construction, you can see that this gives SL2 invariant theories for any manifold. Thank you.
So, why isn't this a construction over here? I mean, you told us a prescription for how to compute the path integral over.
This is a well-defined theory.
Okay.
I mean, in the ADS side, I have to specify all the boundary data ranges, so that for me that's
It needs the string construction? Or?
not really. So there's a more mathematical formalism called relative continuity theories. Well, basically based on these ideas of Witten, but formalized by Fried and Telemann, in which you basically don't care about ideas too much and just think about Chersenov theory. So, yeah, because one problem is that You want to work it to a different manifold, you want to do this freedom element. That's for my question. If there's in terms of areas of just to make it more familiar.
And in AST, in the reading between the lines paper, there was a statement that they made that excluded this possibility by some statement that the 4D analog of modular invariance would require a kind of a...
Yeah, I'm not sure I agree with this. I mean, I can't explain to you why. Because I'm maybe wrong, I'm sure I understand. There's one important thing. Many of these arguments have in the back of the mind that the theory should give concrete predictions just by saying, I have theory, and then you give me a manifold and I can tell you an answer for them. This requires one extra step, so I tell you, I have a way of constructing theories, you give me a manifold, I give you a bunch of theories and you choose them on papers. That's the behavior of the 0,2 theory. So when people say 0,2 theory is not a theory, it's something else. And this is also something else. Because it requires a choice. Or in a manifold, you need to choose a polarization. Now, some of these I suspect are equivalent. For example, for K3, the symmetry is very big, so I suspect any splitting of this kind would be asymmetric. If you formally you're putting a 1 here or 1 here,
But you're saying for a general four manifold, there may be kind of topologically inequivalent choices of I that do this splitting.
In principle, I don't know an example.
So in particular, what you have done, does it imply that you can put a supersymmetric theory in any four manifold, any course for supersymmetric theory?
Well, yeah, I chose,
Spin.
I chose it to be spin for that reason.
Yeah.
Locally, I want the same thing, so the conditions you impose for ensuring supersymmetry will have a player of the don't, but this doesn't change. This doesn't change that. This is a global data.
Right.
Oh,
I see. So in addition, you will need that locally you can...
Yeah. The manifold must be a manifold where you can put it in positive. But that's a local condition.
So you said this also worked for Zn as well as Z2.
Yeah. That's a problem. Yes.
What?
That's
that is, yeah, for Z2 it was sort of easy because E8 was an even self-dual lattice. What magic makes it work for arbitrary n?
So if I understood, you don't actually know how to prove it for arbitrary n.
No, for arbitrary n. I can prove it. So I can prove it for any prime n.
Okay.
I can prove it for any odd n smaller than 10 to the minus 10 to the 5.
Okay.
I can prove it for any n which is 4k plus 2 is smaller than 10 to the 5. The 10 to the 5 is done because my computer is not getting hot. And I can prove it for any equal to 8. I suspect it's true for n.
Okay.
So you have it for, I'm sorry, odd n, 4n plus 2, but not 4n.
No, but I think it's a technical abstraction because the first two cases, 4 and
8 work.
So is the smallest n for which you need double square?
Well, maybe Ben has done it. The combinatorics of the derivative is very smart, for instance.
Can you find the explicit form of the question function, or can you just prove that it's...
Yes, so in all these cases I mentioned, I don't have explicit change of basis. And it's in the case much easier to prove that the partition function is just invariant against the vertical derivative.
Is there something different on CP2?
Yes, because CP2 is not a spin, so I cannot argue that this guy is the square of a number is an even number. In fact, in CP2, the square of the hyperplane is 1, not 2. So then this story doesn't work. But I haven't really thought carefully if there's a way of making it work.
So maybe you can do some spin C version of this.
Yeah, that would be one thing. siempre es más
You started with saying that you could put the 2B string on C2 mod ZN. And in that context, is there a translation for what this data is?
Yes, and that's very interesting because typically we think of type 2 string theory as a well-defined theory. But in principle it isn't, because it has a circular factor. So in principle you have to do this game for variables. Now, people don't pay attention to this because if you put type 2 string theory in a manifold which is compacted, then automatically on spin intersection form behaves in such a way that's unimodular. But C2 mod C2 is an exception to this. The intersection form C2 mod C2 is not unimodular, it's just 2. So it's 2. So type 2B string theory on C2 mod C2 requires a choice. I don't know physically what the choice means, but you have to associate the chance theory to it, context. The thing that's not known, obviously I don't know, is what this chance theory is. In principle you have to choose. It's not well. So the same problem you have in the 0.2 theory of type AN, you already have in 10 dimensions, not 10 dimensions. As far as I understand, in the next slide.
If there are no other questions, I thank you, Inaki.